So the temperature is directly proportional to the average kinetic energy of the molecules. So we can look at this in a couple different ways. So down here we have our kinetic energy, average kinetic energy, and ignore that subscript. That should say AVG for average. Somehow became Greek. Average kinetic energy is 3/2 RT. So we have our average kinetic energy directly proportional to temperature. This one, when we look at the units, okay, for R, don't have it written down here, R has to be in joules. R will be 8.3145 joules per mole Kelvin. So when we multiply by Kelvin here, the Kelvin will cancel, and we're just left with joules. At joules per mole. So this equation gives us the average kinetic energy on a per mole basis. The energy of a gas molecule itself is energy equals 1/2 mass times velocity squared. Well, the particular type of velocity that we're going to use is called the root mean square velocity. So it's an average velocity. It gives us what we need in this process, and we use the letter U to represent that. We're using letter epsilon to represent the kinetic energy of the molecule. So energy of a molecule is 1/2 mass times velocity squared. The energy of a gas here, this equation is on a per mole basis. If we want to make it on a per molecule basis, all we have to do is divide by Avogadro's number, N sub A, Avogadro's number, and that will give us joules per molecule. Okay, so we combine these two equations up here. We're going to rearrange, solve some things around, and we end up with the root mean square velocity of a gas molecule is the square root. This square root should have a line all the way across to the parentheses, close off the parentheses. It's 3 RT over the molar mass. So we can get the velocity, average root mean square velocity of a molecule, relating it to the temperature and the molar mass of the gas. So as we increase temperature, the speed is going to increase. As we increase mass, this is in the denominator, the speed will decrease. So increase in mass will mean a slower velocity. So in this case, we're going to see that the velocity of the molecule is going to change with molar mass. The energy of the molecule does not change with mass at all. So the identity of the molecule does not matter for the energy. The identity does matter for the velocity. So velocity is square root of the whole 3 RT over molar mass. And so we're going to, in addition, be able to use the equations here. Also know that when we look at a gas mixture, the gases are going to all be at the same temperature, all be the same average energy, but the velocities, the lower mass gases will have the higher velocities, and the higher mass gases will have lower velocities. This will play into two properties of gases coming up. Effusion and diffusion, those are the two properties that will, where the molar mass and the velocity will be affect the property. So here's the gas constant in terms of joules. So this is what we're using for these equations, since we're looking at the energy of the molecules. So gas constant is 8.3145 joules per mole Kelvin. And for these equations, we really want to use SI units for everything. So SI units. So our molar mass here, in terms of SI units, is going to be kilogram per mole. That way, when our units are canceled off, now we're going to end up with a kilogram meter squared per second squared, but that's a joule. So if we use the SI units for each component, we'll get SI units coming out of this also. So effusion is the process of a gas leaking through a pinhole into a vacuum. And we can look at how fast the gas is leaking through the pinhole. So that's the rate of effusion. And the rate of effusion is inversely proportional to the square root of its molar mass. So we saw the velocity of a gas is inversely proportional to the square root of its molar mass. So the rate of effusion is proportional to its velocity. So rate of effusion is just proportional to a gas velocity, which means it's proportional to 1 over the square root of the molar mass. Well, the easy way that we do this is we use one gas to help us to figure out a second gas. So our rate of fusion of one gas over the rate of fusion of a second gas is going to be equal to the square root of the second gas's molar mass divided by the first gas's molar mass. So it's an inverse relationship between rate and molar mass. So you see our numbers here are switching between denominator and numerator. And for the general concept here, low molar mass will be a faster velocity and a faster rate of effusion. It will leak through the pinhole faster than a higher molar mass will. Diffusion is just the mixing or spreading of a gas. It also works for liquids, but it's the mixing or spreading of one gas into another. So if we put a little lemon into tea, we normally stir to mix them up. If we don't stir, they will mix by diffusion. It's a slower process, of course. So for gases, if somebody walks into a room with perfume on, then they stand still. We don't have a fan going. The perfume will still spread through the room by diffusion. So the perfume molecules have the same temperature and average kinetic energy as the air molecules. For air at room temperature, that's roughly half a kilometer per second is the velocity. So they're moving pretty fast. They're having a high number of collisions, about 10 to the 10 collisions per second. And then the average distance between them is about 60 nanometers. That's the mean free path. So the perfume molecules are just moving. They're getting moving fast, but they're having a lot of collisions. So they're just slowly being mixed in with the gases and will slowly work their way throughout the whole room. That is the process of diffusion. Now, what we call real gases are gases that fail to obey the ideal gas law. And luckily for us, the ideal gas law works for most gases under normal conditions. They will fail under high pressure and low temperature. So the higher the pressure, lower temperature, the more we start to deviate from the ideal gas law. And that's because gases really have volume. Our kinetic molecular theory treated the gas molecules as a point, volumeless point. And gases have attractive forces, and when they're moving slow enough or they're forced close enough to each other, they will start to feel those attractive forces. And when they do feel those attractive forces, they're now moving not in straight lines, but in curved lines as they are pulling around the adjacent molecules. There's a variety of ways that we have dealt with real gases. The van der Waals equation is the most popular of these. So there are two new terms in the van der Waals equation, A and B. These A and B terms are terms that are measured experimentally for each gas. So now we have to identify the gases present. So if they're feeling attractive forces, if they're feeling the effect of the volume of the molecules, then we need to know the volume of the molecules or how strong those attractive forces are. So that is what we're doing with these factors A and B, is experimental measurement of the attractive forces or the volume of the molecules. So we have two ways that we write this equation. The first one up here is keeping the ideal gas law equation. So we got pressure times volume equals nRT. So the pressure comes with a corrective term now, pressure plus A times the square of moles over volume. And then volume has its corrective factor now. So it ends up being volume minus moles times B. Or we can take this equation, solve it for pressure. And we get pressure is nRT over V minus NB. That whole term minus A times N over V squared. So van der Waals equation is an easy equation to solve for pressure. It's a difficult equation to solve for volume, since volume is in two spots up here with a cubic component, and it's down here in two spots also. Volume is difficult to solve in this equation. So A corrects the pressure, and A corrects for the attractive forces between the molecules. It ends up reducing the pressure. The attractive force reduces the pressure. So if the molecules are attracting each other, they will curve, which reduces how much force they'll hit on the wall when they hit the wall. And this reduces the pressure because we're adding in with the total pressure for the pressure from the ideal gas law. But now this will take away from what the ideal gas law will give us, giving us a smaller pressure for the gas. The corrective factor B on the volume is for the volume of the gases. So we're adjusting for the volume of the actual gas molecules. And this one ends up having an effect of reducing the pressure. We can see that down here. So as B increases, not reducing pressure, increasing pressure. It increases pressure. So as we have a greater volume, there's going to be more collisions. And as B increases, this denominator decreases, which means the fraction increases, giving us a higher pressure. So B increases the pressure, whereas A decreases the pressure. So we're going to see these effects at high pressure and low temperature. See, so larger volume molecules will deviate from ideality quicker than smaller molecules. Molecules with strong intermolecular forces are going to deviate from ideality quicker than weaker intermolecular forces. And the intermolecular forces, the easy way to look at that is the boiling point. A higher boiling point means higher intermolecular forces. So it means that higher boiling points is going to be quicker to deviate from ideality. Gas equation for the chapter, which means that we are at the end of the chapter. and the constant. So here's the ideal gas constant, and there's two forms. The top form we use for the ideal gas law, 0.08206 liter atmospheres per mole Kelvin. And then for the energy equations, we use 8.3145 joules per mole Kelvin. And that's the SI units also. So that'll be the SI units for the ideal gas law, ideal gas constant.